We've been studying the gas laws in terms of a volume, a pressure, and a temperature. And so what we're going to do is we're going to be taking a look at those values, but asking a slightly different question. You see, when we're doing the gas laws initially, we're asking what would the new values be if we change some conditions. So the combined gas law is asking my P1 and solving for P2 and so on. But now we're going to be asking a slightly different question, which is how much gas is present. Okay, so we might say how much in terms of grams. And so that's what the ideal gas law is going to do for us. Certainly you can ask that same question when we're doing combined gas law, but this will eliminate a lot of the work, and I'll talk about that as we go. So what we're going to do is we're going to be taking a look at an experiment where we take a standard, just regular old lighter, a butane lighter. I stripped off some of the mechanisms that would tend to catch some water. And so I stripped those away to make it a little bit easier, a little bit more accurate results. And I just basically immersed it in water and I dried it off as best I could. And I found that that lighter had a mass of 12.90 grams. Okay, now this is a butane lighter, which means that inside is in a liquid form because it's pressurized, but it has a chemical formula of C4H10. Now, I collected this gas through a process called water displacement. So what I had was a graduated cylinder that I filled up completely with water, and I have it immersed inside of a bucket of water. And that water is, by the way, 21.9 degrees Celsius. So I lifted it up, the graduated cylinder up, I snuck my lighter out underneath a little bit, and I depressed the lever of the butane lighter, and I released 72.3 milliliters of gas. Now, to make sure I had 72.3, you'll notice that it's not the full graduated cylinder. It's not all the way full with gas. I actually left a water column in here. So I have to make sure when I'm doing this experiment that the water level right here has to match the water level on the inside of the bucket, because as you push down, it'll actually compress that gas. If I lift it up, it'll actually allow the gas to expand out. So I needed to make sure that the volume, the water level on the inside of this cylinder matched the water level of the inside of the bucket as well. Then I read this. Now, I need to convert that into liters for the ideal gas law to work. Okay, before, as long as we started in milliliters with combined gas law, you could keep it in milliliters. But for ideal gas law to work, I must convert that to liters. Now, as I said, the water temperature was 21.9 degrees Celsius. Now, we're going to assume that the gas temperature is the same because I bubbled the gas up through that water, so the temperature of the gas would be the exact same, and I'm going to convert that into, as we're used to with gases, I'm going to convert it into Kelvin using this formula. You should know this formula by now. Now, the last thing I had to do is figure out the pressure of that gas. And we need to be careful here because the pressure, we could stick a probe up there, I guess, but that throws off the volume. But the pressure of this, I can determine in a different way. Remember when I said that I got the two water levels equal? Well, that meant that the pressure inside the tube, if the water level matched the level of the bucket, that the pressure on the inside of this would match the atmospheric pressure as well. That's what it means when those two water levels are equal. Well, I just looked this up on my phone, and I found that the atmospheric pressure in this area was 100.61. But I need to be careful here, because that's 100.61 kilopascals total. And on the inside, I don't know if you can see this, but it is a little foggy inside. That's because I collected this gas by water displacement, which means it's not just butane in here. It's also water vapor. And so the water vapor I need to subtract off using Dalton's law of partial pressures. I know that the total pressure is the sum of its parts. So I use a vapor pressure table, and I just look up, because the gas is 21.9, I'm going to call that 22. I see that 22.6 kilopascals is my water vapor pressure exerted at 22 degrees Celsius. So I know inside that cylinder, 2.6 kilopascals of this total pressure is just water. So what that means is the butane accounts for the rest of that. Dalton's law of partial pressure will tell us the individual parts. Okay? Now I have the components to figure out the mass of the butane gas that's in that cylinder. Okay? Now, I could do one way, which is a really long way, but it does work. I could ask a question very similar to what you're used to at this point using combined gas law. I could say, I'm at this condition and this condition. What would that new volume be if I moved this to 273 and 101.3 kilopascals? I could do that. I don't need to do that, but I could do that and find my V2. And I would know if I'm at STP, then my V2 is in liters, then 22.4 liters of any gas at standard temperature and pressure is 1 mole. then I could go moles into grams. I don't need to do all of that work, that roundabout way. This is what the ideal gas law is all about. It does all of that work for you. All right, so here's your ideal gas law. It's Pivner. We need to make sure that our units are correct. Now, first of all, we need to just have, if I'm collecting this over water, I need to have the dry gas. So this is going to be in kilopascals. My volume must be in liters for this to work. My temperature, yeah, we should be used to Kelvin by now, okay? And I want you to be careful here because my N value does not answer this question. This stands for the number of moles of butane, which is C4H10, okay? Now, all of that work I said in combined gas law, assume STP, find your new volume, then convert your volume into moles. Yeah, that's what this magic number of 8.31. That's what that mathematical constant does. 8.31 is your math constant. When we're doing all this, that will move everything to standard temperature and pressure, apply your 22.4 conversion, and that 8.31 is what is actually going on with the equation. So let's pop in these values. This is what I want you to do at home. I want you to take a look at the kilopascals. Pop that value in here for P. Your liters, pop it in here for your V. You're going to pop in your temperature value in Kelvin right here, apply your 8.31. I want you to figure out how many moles of butane. Now, let's look at the question. I want to know how many moles of butane are in this cylinder right now. Now, I want you to ask the question, how many grams of butane are in that cylinder right now? How do you do that? Well, remember, you have 4 carbons, you have 10 hydrogens. Carbon is 12, so this is 48. Hydrogen is 1, so this is 10. So what we just found is that the molar mass of butane is 58 grams per mole. Now, be careful, because this is all mathematical, okay? I collected some data, but I just applied it, and so this is all in theory. Theoretically, I want to know how many grams of butane are present. Now, I also want you to figure out your percent yield. Okay? Now, we're going to take this lighter, we're going to figure out, remember that water has a big mass to it, and I want to dry it off as best I can. This is the same procedure I used in the first place. All right, so now we started at initially a mass of 12.90. Now, I have an ending mass of 12.84. So the question is, how many grams, if I get rid of some of this mess on the side, now that we've taken all of that, I want to know how many grams of butane actually. And I want you to compare that theoretically. Okay? Remember what percent yield is. I want you to find also my percent yield on this experiment. Okay? So you got to do some math here to figure out how much was actually obtained. Now remember, this is by putting the lighter on there. When we apply the math to it, this is theoretical work. Okay? So remember how we do percent yield? Those are the 2 things that are part of your assignment. Good luck.